Hello, welcome. Today we're learning about normal distributions, and normal distributions are described by a special family of bell-shaped symmetric density curves. Now, they look like this down here. See how they kind of look like a bell? That's a normal distribution. They have the same center. The center is mu, and their spread is described by their standard deviation. They have the same overall shape. So every normal distribution, if you describe something by a normal distribution, everybody knows what shape that is. So now, if we look at the break, one standard deviation always happens at this point. We call it the inflection point. It's the point where it goes from concave down to concave up. It's also used fairly common in calculus classes. But that determines where the one standard deviation is. Now, there's a rule in statistics, or in with normals distributions, where it's called the 68, 95, 99.7 rule, and it's also called the empirical rule. It's empirical rule. Now, what that says is approximately 60% of the data is within one standard deviation of the mean. Approximately 95% of the data is within 2, and almost all of it, 99.7, is within 3 standard deviations of the mean. So if I drew a line straight down the middle here, we know that 68% of the data is within 1 standard deviation above and below the mean. So that means about 34% is on each side of that. And if we know 2 standard deviations, it's 95 from here to here. If we cut that in half, it's about 47.5. That's going to be the distance between, what percent is between 0 and 2. So if I subtract that from 34, you'll find that about 13.5% of the data is between 1 and 2 standard deviations. And since it's symmetric, about 13.5% of the data is over here. Finally, we have 99.7. So that's almost all of it. But if we go from the middle to up, that's 49.85. Now if I subtract that from 47.5, that's 2.3% of the data. So 2.3% of the data is here. Now if you add all those, get pretty close to 100%. There's just a little bit on the outsides. 0.3% is on the outside, so it's 0.15% would be over here, and 0.15% would be over here. Now we can use these numbers to solve problems. Women between the ages of 18 and 24 years old have heights that are approximately normal with a mean of 64.5 and a standard deviation of 2.5. First, let's draw this out. So I'm going to start with my line, and I'm going to draw my normal density curve above it. And now, if I know the mean is 64.5, I'm going to go 1, 2, and 3 standard deviations. And so that's going to be, what, 67, 69.5, and 72. Now, if I go backwards, this would be 62, 59.5, and 57. So those are our standard deviations. Those are what we call the x values. If I wanted to use the z-scores instead, I could just have 0, 1, 2, 3, -1, -2, -3. It doesn't matter if we do this in x values or z values. The graph looks the same. But now, when we say what height is approximately at a 97.5 percentile? So coming up from the bottom, we know percentile is at or below. So the 50th percentile is here. And if I go up to the next one, that's 50 plus 34. So up here, I get to so this is the 50th percentile. This is the 84th percentile. So we have to keep going. So what do we say? We're going to have to add another 13.5. So if I had 13.5, I get up to 97.5. This is the 97.5th percentile. So that means that the 97.5th percentile is 69.5. I have to read my own writing. Inches. So let's do another one. What percentage of the heights are lower than 62 inches? So if I come out here, lower is from here to the left. So I can look at my normal chart. Lower, that's from -1 and to the left. From -1 and to the left, we can just add up these numbers. 13.5 plus 2.3 plus 0.15. It looks like about 16, or mine says 15.95% of the data is less than 62 inches. Finally, what percent of the heights are greater than 62 inches? So if I look at 62 inches, it's over here. I just go from where I was before and to the right. Now I could add up all of these, or I could take 50, because from here over is 50, and add 34. That seems pretty reasonable. So 50 plus 34 is 84%. All right. Hopefully you can do the on your own.